Chapter 7, Transverse Shear Nail Spacing, example number 2. In this example, we have a condition which a configuration which consists of four boards nailed together, and if the capacity of each of the nails is 100 pounds and the vertical shear applies to the system is 700 pounds, we want to know what is the distance between these nails and also S prime here. So they are kind of there are two sets of nails with the same capacity, the same material, different spacing. If one of them connects the uh, top flange to the web, as you can see here, one of them connects the top flange to the web, and the other groups of nails connect the extra addition part of the flange to the top flange. So there are two kind of extra parts attached with the nails to the top flange, and they are at the spacing of S. So two sets of nails with the same a capacity and different spacing. Let's see how we can approach this problem. So in this kind of shear problems, the equation is n times f nail is equal to vq over I times s. N is number of nailing for the unit of area, and then F is the capacity of nails which is provided in problem statement. V is the shear which is also provided. I we need to calculate moment of inertia. First moment of inertia Q, which is equal to A prime times Y bar prime. We need to calculate this one as well and then replace in the formula to get the spacing of nails from each other to know how uh, those nails should be apart from each other to handle the shearing force on attached part. So first of all, let's calculate the centroid board for the system. If we keep the bottom of the section as a base for us and just move forward, upward for centroid calculation, and the formula for centroid is y bar is equal to summation of area times their own centroid. For example, this part for its own, this part the web for its own centroid, and over the entire area. If you do so, it just gives us the centroid is equal to 7 Y bar is 7.6452 inches from the bottom of the section. So that gives us a numeric value of centroid. You can easily see the distance of the center of each part to the centroid. So for example, for the web itself, this is the center, which is at the height of 5 inches. That's 5 inches. And the other one is at 1.5 inch from the top, and this is the distance of the centroid to the centroid of the entire system. So the other component of this problem is the moment of inertia calculation, and if you calculate the moment of inertia, it just says if we call this part the top flange is I1, then I2 is 2 off up to here, then 2 of these I2, and plus the web, which we call them I3. So we have a top flange like A1. We have 2 of this extra part to top flange, which we call them I2. And there is a web at the center, which we call that I3. And if we just add them together, use the parallel axis theorem, for example, for I1, that's a 112 base cube height, and that's I1 112. Base is 10 inches and height is 1 inch. That should be 112 base cube height. So we started from depth, I think that's 1.510 cube, then plus AD squared. Yes, it just, my bad. This is, consider this for I1 and this one for I3. So if you can see here, that's 11210. Yep. So that's a I1 is for the depth. So I1 is for depth and I3 is for top flange. And the two I2 are the two extra part at the sides. And also we need to use the parallel axis theorem, which is AD squared. A is 1.5 times 10, which is the area of the web, then D squared is the distance of the web to centroid of the entire system, which you can just cut it off by 2.64, and AD squared, that is squared number, and so on for the other part to get the numeric value for I, which is 300. Moment of inertia for the entire system is 337.43 inch to the force. And as soon as we have a centroid and moment of inertia, we can simply move on and calculate the rest of the problem. So for example, if we just want to go for distance between extra part of the flange in terms of nail spacing. So it just gives us, if you just look at the cross section for the unit of length, don't look at to the board. Just consider if you want to apply a force, a stress, which separate the extra addition part of the flange from the top flange itself for the unit of length. So we cut it off just by the unit of length, forget about the total length, and just the cross-sectional area is A prime, and that's a height times a thickness, and that's a 3 times 1 inch squared, and they are attached with only one of those nails. So that goes by number of nail is 1, force of nail is 100, a V placed from problem statement, which is 700 in terms of shearing force, that's 700 here, and over I we just calculate I to this number, and then just look at the configuration. If we want to apply a stress due to a bending moment and separate the extra part from the top flange, that's how we see. This is our cross section for the unit of length. Again, that's a unit of length, and then we want to apply, this is our cross section, which runs all the way, drives all the way to total distance of top flange, which we don't care because we work with dx, and that's for unit of length. So our area is just a inch squared. And then for placing in the equation, it just gives us q, the q, which is first moment of the area, that's a prime times y bar prime. We know what our area is from the previous part, and our y bar prime is the centroid of this additional part, which is attached to this flange, and the centroid of that part to the centroid of the entire system, which is 1.8548. And if you place that in the equation, it just gives you distance of nail spacing in extra part to the flange, or it should be equal to 80.66 inches apart from each other to hold the entire shearing on the top flange. And also other part, which is S prime. So far we calculate the distance for this part, and now we want to know what is the effect of distance in S prime. So again, for S, we just get the 8.66 inches in terms of nail spacing. Now we want to know what is S prime for connection of a flange to the web itself. So let's see. So if you just take, for example, one of those nails, the web just drops down. So that's how we can see the effect of the attachment by nailing. So again, if you look at the cross-sectional area, it just says a one of those nail. Again, we don't care about the total length, which is x. We just for cross-sectional area for the unit length. So one of the nails just owns this part, and so we just replace for n is equal to 1. Then force of nail, which is the capacity of nails, 100 pounds, and 700 times q over the of inertia times s prime this time, distance of nailing and of connection between flange and web. So this is again the connection of flange and web with each other, and that's one of them is responsible for this cross-sectional area. So if we call that A prime, that's again height of web times the thickness, so that's a 15-inch square. And for a y bar prime is this distance of the web, which is centroid of web. It's at 5 inch from the bottom, and centroid for the entire system we already calculated. That's 7.6452 inches. So this distance is just translates here, and if you place in the equation, it just gives us a distance of 1.2 inches. And so if you remember, the other nailing spaces is something like 8.66 inches, and this one is 1.21. It just says the importance of nailing which connects the flange to the web is far important, and they should, if we are using the same kind of the nails, because the capacity was the same, so they are identical, so the distances of the connection between web and flange are much closer than the extra part, because that's more important. Thank you. We solve more problem on this chapter. Thank you.